Awesome. So let's get started with the proof. I will start with some of the setup and the definitions. So first, what is the Bellman operator or T in this case? So if you have implemented value iteration, you will recognize that the Bellman operator T is just a one-step update for the value function. So the Bellman operator is very simply just a recursive formulation for computing the expected discounted sum of rewards. And this is a one-step update. And the Bellman operator T returns an improved value function, which is the input to T. Now, the infinity norm is very simply just the maximum absolute value of the input to the infinity norm. So typically, you will provide a vector as an input to the infinity norm, and the output is just a single value which corresponds to the maximum absolute value of the input vector. Now, in this proof, the reason why we use an infinity norm is that it acts as a proxy for distance. And now let's understand what a contraction or a contraction mapping is. So in this example, let's take a look at this equation. So let's assume that we have a function f, which is a contraction mapping. Then this expression tells us that when we apply f to inputs x and y, the resultant distance is less than or equal to gamma times the distance between the inputs. And here gamma is between 0 and 1. And hence, what the contraction mapping definition tells us is that applying a contraction mapping F causes the distance between its inputs X and Y to continuously contract and shrink. So basically, if we apply this contraction repeatedly, the distance between the inputs keeps on shrinking, and it sort of gives us convergence behavior, where in every application of F, you are shrinking the distance between its inputs, and it eventually converges to a fixed point, and we will we will see more of that. Now, this diagram is a really nice illustration of this contraction property, where we see that the distance between the inputs keeps on shrinking, and it finally converges to a fixed point. Awesome. So now in this video, we will be looking at two things. So this is a two-part exercise. The first is that we will prove that the Bellman operator is actually a contraction. And secondly, we will see what the consequences of this are. And we will just take a look at the Banach fixed point theorem, and we will see what are the properties that this contraction has, which which really is exploited by reinforcement learning and value iteration. Awesome. So now we first need to prove that the Bellman operator is actually a contraction. So here, this is just a definition of what the Bellman operator does. And this line corresponds to exactly what we need to prove. So this is again just a definition of what a contraction is. So basically, we will be proving that T is a contraction, and in order for T to be a contraction, um, the distance between V1 and V2 upon application of the Bellman operator should shrink uh, at most by a factor of gamma. Awesome. So the first step of this proof would be to expand the definition of T inside the left-hand side of the expression that we want to prove. So once we make use of the definition of T, we get this gnarly looking expression. And just to make this video more concise and actionable, I have done a lot of the steps and the computation so that we can just talk about the general outline and the thought process of each step. So once we have this expression, the the most the thing that we can start off in terms of the simplification would be to deal with these max over actions. So so let's try to see how we can actually take this outside. Okay, so the way that we can simplify these max over arrays is to take a look at this very nice um, relation that we get. So basically, the way that this reads is that let's say we have two functions f and g, which are parameterized by I. And let's say we take the individual max over i's of these two functions, then the individual maxes and the difference between the individual maxes will always be less than or equal to the global max of the difference between f of I and g of I. So we can actually leverage this very neat relation to take the max over A's outside. And once we take this outside, this actually the left hand side is now upper bounded by this expression, which and this expression is just a simplification of the expression that we had above. And some of the simplifications that we made are that since we have this minus sign over here, we can yeah, the rewards get subtracted out, and also we can take the gamma times the sum over probabilities. We can actually take this outside, and then this is then multiplied by the residual of this expression, which is just v1 of s prime minus v2 s prime. Now the next steps of the proof get easier to follow. So we can just make use of the definition of the absolute value to give us this relationship. So what this means is that we know that the absolute value of the difference between V1 and V2 will always be greater than or equal to the regular difference between V1 and V2. So we can define this clear upper bound to this difference, and then this expression basically can be bounded by this new expression, which here the only thing that we've done is that we have replaced the regular difference of V1 and V2 by the absolute value difference of V1 and V2. And then next, we just make use of the definition of the infinity norm, which is the maximum of the absolute value of a vector. So this actually gives us this gives us a nice relationship where we can upper bound um, this expression by this new expression that we will be writing over here just by making use of the definition of the infinity norm. So this is upper bounded by the max over A gamma times this sum of probabilities. And here we have the infinity norm of V1 S prime and V2 S prime. And you can start to take a look at how this now is starting to get closer to what we needed to prove in the first place. And just to give you a preview, we can essentially make use of the fact that the sum over probabilities, this actually sums to one. So there is a further simplification that we can make since probabilities over partition sum to one, we can we can replace we can replace this uh, we can replace this by one. So we have over here. So yeah, we have the max over actions times gamma times the infinity norm of v1 s prime minus v2 s prime. But now that we have removed this sum of probabilities, we have this s prime, which no longer makes any sense in this expression. So we can actually simplify this further. We can basically examine the fact that that this expression parameterized by s prime will always be upper bounded by the infinity norm of v1 minus v2, the vectors itself. So yeah, let's make use of this fact to essentially get rid of the s primes. And now what we have is a much more cleaner expression. So we can take the infinity norm of simply v1 and v2 of v1 minus v2, and we can also simplify this even further uh, because the max over A also does not make any sense now that we have simplified the sum of the probabilities to one. So in fact, we could have got rid of the max over A um, in the previous step itself. But yes, basically this we can also get rid of the max over A because it's upper bounded by what we now have, which is simply um, gamma times the infinity norm of v1 minus v2. And this is exactly equal to what we needed to prove above, that the Bellman operator is a contraction. So we needed to arrive at this right-hand side expression and over a series of simplifications, which basically just involve expanding out the Bellman operator and then just making some straightforward simplifications over probabilities, and also by leveraging some neat comparison tricks, we have arrived at what we were supposed to arrive at, and hence we have actually proven that the Bellman operator is indeed a contraction, and it is a contraction of gamma. So we can say that the Bellman operator is a gamma contraction, which means that it shrinks the distance between its inputs by a factor of gamma at every step or iteration. And this is a significant result. Now, this proof offers a really interesting practical insight about this term gamma, which is the discount factor, and this controls how much we discount future rewards. So now that we have proved that the Bellman operator is a gamma contraction, we get that upon application of the Bellman operator, like so, the distances shrink by a factor of gamma. Um, And what this means now is that let's say we have a really high value of gamma, which in this case, since gamma is between 0 and 1, this could be a value of gamma around 0.999, which is close to 1. The difference between this this difference, which is a new difference, and the old difference is very less because gamma is close to 1. And hence, the Bellman operator is not really shrinking the value function by a lot. But on the other hand, when we have gamma as a very small number, then we know that that this distance would be would there would be a big difference between the left hand side and the right hand side, which means that the Bellman operator is shrinking the value function really rapidly. So this tells us that gamma also controls how quickly the Bellman operator contracts the value function. So if we have a high value of gamma, then it takes a more number of iterations to converge. And on the other hand, if we have a low value of gamma, it converges quickly because the contractions happen quicker. And now, finally, that we have proven that the Bellman operator is a gamma contraction, this has some really interesting implications. So first off, a gamma contraction implies value iteration convergence to the optimal value function. And we get this by something called a Banach fixed point theorem, which basically states more generally that for any contraction mapping, there must be a unique fixed point. And no matter where you begin from, by applying the contraction, you always converge to this optimal fixed point. So that's actually pretty remarkable because what this means in the context of value iteration is that like we're guaranteed to have an optimal fixed point called V star, which is the optimal value function that we converge towards. And no matter the initialization or our starting point, the Bellman operator guarantees that that the value function will converge to this fixed optimal point. And this is pretty remarkable, and it's a very unique property of Markov decision processes and reinforcement learning and value iteration just exploit this contraction property of the Bellman operator to guarantee convergence to this optimal value function, which is the whole point of doing this activity and of implementing the value iteration algorithm is to find the optimal value function. So this is pretty remarkable, and this is also very significant in modern RL because deep reinforcement learning is just a generalization of the exact same properties that we have studied here, and it's really unique how universal the Bellman operator is, and it applies to almost all modern deep learning techniques like Q-learning, TD, and a host of other techniques. So I hope you found this video instructive, and thanks a lot for listening.